Okay, let's talk about Newton's 3 laws of motion. This is a big deal. Newton is a great man, or was a great man. I mean, he changed the world. It is no coincidence that the Industrial Revolution happened after Newton described his 3 laws of motion to the world. His 3 laws of motion brought order and understanding to the world around us, and really allowed other smart people to come along and do what we call engineering, and to make inventions and so on. And all this thing called engineering, which basically is how humans, it's basically applied physics. It's engineering is how humans use the laws of nature that scientists discover to make practical things. But there really was no good description of nature before Newton. And so his 3 laws of motion really allowed the whole thing, the whole Industrial Revolution, to get started. So let's talk about his 3 laws. The first law is called the law of inertia. It talks about inertia. Now, this is a very simple idea, this idea of inertia. It basically says this: objects don't change the way they're moving unless you force them to. Objects don't change their motion unless you, okay, that's kind of the generic you, unless you force them to. Okay, now that's not a super scientific way of thinking about it, but no, it's pretty good. Let's go back to our little block of wood here. Okay, here's our block of wood. Now, it's at rest, and it's not changing the way it's moving, is it? It's just sitting there. Now, of course, there are forces acting on it. The earth is pulling down on it with the force of gravity. The table is pushing up on it with an opposing force. But these forces cancel each other out. But if I apply a force to the block that isn't canceled out, the object will change its motion. So, whoop. All right, so I applied a force and I changed the motion of the block. Now notice, by the way, that the block changes its motion and it moves forward, but then it comes to a stop. Why does it come to a stop? According to Newton's first law, once this block is in motion, it should stay in motion forever, moving in a constant speed in a constant direction. The only thing is that there's a friction force. There's an interaction between the table and the bottom of the block here that makes it stop. Okay, so this is quite a big idea, this law of inertia. Objects don't change their motion unless you force them to. If you go out into outer space and you were to have a baseball in your hand out there in outer space, and there were no planets or any gravity fields nearby, and you threw that ball into space, what would happen to the ball? Well, the ball would move, it would move with a certain velocity, right? A velocity has a magnitude and a direction. And you know what? It's going to move at a constant velocity. That is a constant speed and a constant direction forever, unless it runs into something. Unless it interacts with some other massive object nearby, like a star or a planet, that is going to change its path, that's going to apply a force to it. You need a force on an object to change its motion. So that's the first law. Okay. His second law is the law of acceleration. Now this is a law that is best expressed in an equation. So I'm going to write the equation down. But I want you to understand what the different parts of the equation mean. And by the way, this is using Newton's second law is a whole branch of physics and engineering in and of itself. So this is really important. So the second law says that if you have a net force on an object, that net force will cause the object to accelerate. And the amount of acceleration depends on the mass. The more massive an object is, the more difficult it is to change its motion, the more inertia it has. And so therefore, for the same force, you'll get less acceleration. And it will also say that the acceleration is in the same direction as that net force. Now we'll talk about what we mean by a net force here in a minute. But so that's a lot to write down, and I'm not writing it down right now, I'm just saying it out loud. So that's too much to write down. My hand, look how little my pencil's getting. I just don't have enough lead to write all that down. So, or graphite. So what I'm going to do is I'm just going to write it as an equation. The net force will cause an object to accelerate. Okay, let me zoom in here so you can really see this. The net force on an object causes an object to accelerate. And the amount of acceleration you get depends on the mass. So this is mass measured in the metric system we use kilograms. Excuse me. And this is acceleration. The A stands for acceleration like it did before in meters per second squared, or meters per second every second. And of course this is force right here. So what we're saying here is that if I apply a net force, that is a force that isn't being canceled out by any other forces, to an object, and here's our object, and all objects have some mass, that object will accelerate. And it will obey this equation. This equation describes what causes things to accelerate. Now, in the first unit, or the first couple units we did, we talked about, well, in Unit 2 we talked about acceleration, right? But we didn't talk about why things accelerated. Well, here's why things accelerate. There are net forces acting on them. This is considered by most physicists the most important equation in all of physics. The net force, and I'll put a vector hat on it because force is a vector, is equal to an object's mass times its acceleration. Okay, and this is a big deal, and you need to memorize this equation. You need to know this. Okay, now this is such a big part of what force is all about, is that we have really used the units we've already developed for mass and for acceleration to give us the unit for force in the metric system. So this is, a mass is a kilogram, acceleration is a meter per second squared, and so these units together are the units for force. And what we've decided to do is to name these forces, to name this collection of units a new unit. We're going to call it a Newton. A Newton is a kilogram meter per second squared, and we abbreviate it with a capital N. So really, 1 Newton of force is the amount of force you need to accelerate an object that has a mass of 1 kilogram at a rate of 1 meter per second squared. That's what 1 Newton of force is. And we're going to do some experiments, and you're going to get a sense of how much force a Newton of force is. It's really not very much. I mean, this little block of wood is maybe a Newton, probably less than a Newton in weight. So, but anyway, this is Newton's second law. It tells us where acceleration comes from. It comes from a net force. Next, we're going to talk about Newton's third law. Okay. Newton's third law. And this is the law of interaction. Newton's third law is so cool. I mean, it's so important, and it lets us solve so many problems. It lets us really understand the universe and how it works. So, but here's the thing. Perhaps this describes you. I remember one time studying physics in college, and I got so mad because I couldn't solve this problem that I slugged the wall with my hand. Have you ever punched a wall? You ever kicked a wall? Okay, now who wins? Who wins that battle when you punch a wall? I tell you who wins. The wall wins. Your hand loses, okay? I didn't break my hand, but I had major bruises on it, and I broke the skin, and I really felt stupid because it caused me a lot of pain. Okay, now here's what happens. The law, and it's all because of the law of interaction. You know, for every force on one object, there exists an equal but opposite force. Opposite, when I say opposite, I mean opposite in direction. Equal in magnitude but opposite in direction. Force on another object. Now this is what happened when I tried to punch a wall. Yeah, when I let's zoom out here. When I punched the wall, okay. So let's imagine this hand will be the wall. When I punched it, you know, all right. When I punched the wall, yes, I applied a huge force to the wall, but guess what? The wall applied an equally huge force to my hand. Now the wall is made out of materials that can take it, but my hand isn't. So it caused me a great deal of pain. All right, now, and it's also the law of interaction that will, well, think about this. When a truck is moving down the highway, let's draw a little truck here. So here's the highway, okay, and here's some truck, some great big, big old truck, some, I don't know, I'll give it lots of wheels here. I don't know, this is just a major truck. And it's driving down the road at 60 miles per hour or something, and so it's really moving fast. Here's our really fast moving truck. And then here's a bug. Now this is the moment, the last moment for this bug. Okay, this bug is at an end. Okay, so here's the bug hitting the windshield. Okay, and well, someday the bug will be hitting the windshield when this focus. Okay, there we go. It's in focus now. Now this bug is going to hit the windshield, and there's going to be a smack. There's going to be an interaction between the bug and the truck. Now, what Newton's third law says is something that's a little counterintuitive, because if you ask the average person, who experiences the greater force, the bug or the truck? People might say, oh, the bug experiences a much greater force than the truck, because the truck hardly feels it and the bug, gets squished. But that's not true. That's not true. The bug applies a force to the truck. The truck applies an equal and opposite force to the bug. The force of the truck on the bug is equal but opposite to the force of the truck. The bug on I think I got these mixed up. Hold on a second. The force of that's right. This is the force of the bug on the truck is equal but opposite to the force of the truck on the bug. And so even though even though the force on the bug is totally catastrophic, and the force of the bug on the truck is not even noticed, they're still equal and opposite forces. And that's what Newton's third law tells us. So these three laws are, if you understand Newton's three laws, you are a physicist, okay? If you can understand Newton's three laws of motion and how it applies to the world, you are now thinking like a physicist. So good luck with it. And that's the end of this video, and we'll continue with the last one next on the different types of forces.